Hello, welcome to 10.2 day one. Today we're going to learn about what happens when we don't know this population standard deviation. So if we don't know sigma, how do we do our confidence intervals? Well, we still look at our conditions for inference. We look at SRS, that's very important. Normality. Now we just want to check that it's symmetric and single peaked, unless the population is pretty small. And the independence, we will still want our population to be at least 10 times as big as our sample. Now, our standard error, when standard deviation of a statistic is estimated from data, the result is called standard error of the statistic. The standard error is the sample mean of the sample mean. It is standard deviation of the data set divided by the square root of n. Now, when we use standard error instead of the standard deviation, the distribution is not normal. It's called a t-distribution. T-distributions need a degree of freedom n-1. And we use a table which, for AP stats, our book uses table C, but the packet I handed out, it's table B. And in the packet is the one that you'll actually use on the AP test, so that's the one we should get familiar with. Now this is the table that we use. Notice how on the bottom it says confidence level, so it has a bunch of different confidence levels on the bottom. And then it has degree of freedom on the left-hand side. So you find your degree of freedom, which is n-1, and then you move over to the confidence interval that you choose. Facts about the t-distribution. The density curve for the t-distribution are similar in shape to the standard normal curve. Also, they're also symmetric, about 0, single-peaked, and bell-shaped. The spread of the t-distribution is a bit greater than one standard deviation of the standard normal curve. As the degree of freedom increases, the T of K density curve, so that's the T curve, approaches a normal curve ever more closely. And here's a picture of that. The normal curve is the solid line. And if I have a degree of freedom of 9, you can see that this dotted line is really close to the standard normal curve. But so that's if there's 10 data points, would give you a degree of freedom of 9. If there are 3 data points, that gives you a degree of freedom of 2. And you can see that it's a lot wider than our, wider and shorter than our standard normal curve. So our one sample T confidence intervals, if we draw an SRS, size n from a population having an unknown mean, and this should say mu. Confidence level C, a C confidence level for mu is x bar plus or minus t star times s over the square root of n. So this doesn't vary that much from our previous value, where we had x bar plus or minus z star times sigma over the square root of n. Just if we have an s, so that's finding standard deviation from data, then we have to use a t star rather than a z star. So if we have NOx levels of light-duty engines, and this is our data set, let's construct a 95% confidence interval for this. Well, the first thing we want to know is the parameter. Parameter. What do we want to estimate? We want to estimate the mean NOx levels of all light-duty trucks. All right, now our conditions. Does this come from an SRS? Well, you know, it says it's from a random sample. So we say data is from a random sample. It doesn't say SRS. Normality. How many data points do we have? 1, 2, 3, 4, 5, 6, 7, 8, 16, 24. Already we're over 30 once we already got up to 32. So we can say data is approximately normal. By central limit theorem, because n is greater than or equal to 30. Now, observations will be independent. Observations will be independent. Having a tough time spelling today. Observations will be independent because there are more than. Now we got to figure out exactly how many are. I got 32, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 48. So more than 48 times 10, or 480 light duty trucks. All right, so now we have those out of the way. Now we get to the calculations. So for our calculations, we take our formula x bar plus or minus t star times s over the square root of n. Our x bar, we have to plug in all of this data points and then find an x bar. I'm going to pause this and type these into my calculator. Hopefully I typed everything in correctly. I get a mean of 1.33, and now we look at our t star. Well, there's 48 data points, so our degree of freedom is 47. So we don't have a 47, so we go down to 40. We do the one above it. And I forgot what confidence interval, 95% confidence interval. So we look at the 95% column, see where that crosses this column. It looks like 2.021 is our answer. So that's going to be our t star that we're using. So we come down here, 1.33 plus or minus 2.021. Now my standard deviation is the s of x, so that's going to be 0.484. Divide that by the square root of n, so that's going to be the square root of 48. So when I do this, I do 0.484 divided by the square root of 48. Multiply that by 2.021 to get 0.141. That's good. So if I subtract that 1.33 minus that answer, I'll get 1.189. And then if I add it, 1.33 plus 1.1441, I'll get 1.474. So that's our range. That's our confidence interval. So our interpretation, the true mean NOx level in light duty trucks is between 1.189 and 1.474. All right, now we're done. Now when using that table, we want to use the greatest degree of freedom available that's less than our desired one, just like we did there. All right, and that's enough for today. So good luck with homework.